In the news lately, there's been renewed focus on America's critical minerals, especially following Trump's push to ramp up domestic mining and break dependence on foreign supply chains. But do we really have to dig new mines to secure our future? Today, we spotlight ReElement Technologies, a company leading the way in extracting these vital resources from existing waste and recycled products right here at home. Let's dive into how American innovation is meeting this policy moment.
Our largest adversary today in China controls over 90% of rare earth elements, the vast majority of other critical minerals that are needed in advanced technologies, in defense applications, in manufacturing of goods for that we depend on as every day. The choke point in the supply chain is not upstream on the mining side of things. The entire Earth's crust is mineral. Mineral is rock. Rock turns into ore. We are flush with it on this earth. Mining is a somewhat of a choke point here in the United States, but it's not the urgent one from our lens. The biggest problem that ReElement solves today is in that midstream refining piece. China has afforded their monopoly on the economy, on those markets, because of how and where they've refined these rocks, these minerals, these inputs into manufacturing grade, high purity manufacturing grade chemicals or metals at the end of the day. And because of that, they've used a variety of mechanisms to get a stronghold on global manufacturing, on the output of advanced technology applications, because they control that midstream refining process. That makes our national security vulnerable at the end of the day.
So I'd like to hear the elevator pitch of why then ReElement is going to help solve that problem that you've just enunciated.
The technical aspect of it is really where it resides. At the end of the day, these are commodities that we produce and that China produces at large scale. They produce these commodities at a lower price point. The technology that they use is at a high level considered solvent extraction methods. It is a series of highly chemical dependent phases or stages that require harsh organic solvents and acids to do slight pH adjustments to separate and purify elements on the periodic table into pure form. And because of the methods that they use, there's a lot of toxic acidic wastewater discharge and a lot of toxic waste that these produce. I would say their lack of environmental standards, their lack of social and labor standards allows them to produce these commodities at a lower price point than the rest of the world can. Utilizing that same technical approach comes with high capital, high risk. So deploying that here in the United States, I always say we're never going to outdo China by trying to repeat and replicate China. The problem needs to be addressed through innovation. That's what ReElement does today.
Can you kind of paint the picture for me of what specific kinds of minerals we're talking about, what the value streams are they go into, and then how ReElement has re-envisioned the process of extracting those minerals in a novel way that's sort of different from the way China does it?
I'm going to put them in three buckets. I'm going to put them in as energy storage. I will put them into another bucket that is magnet. I will also include semiconductor in there. I'll use a fourth bucket as far as like more niche-y defense material, defense metals, defense elements that go into things like munitions, optics, all of those other things like magnets, batteries, and semiconductors also go into a lot of defense products as well as things like that fuel the energy transition, like battery storage, for example, like wind turbines, like electric mobility, like EV. So those would be the 3 to 4 buckets of downstream products, applications that kind of go into that value chain.
So rare earth and then sort of critical minerals that are not rare earth are resources like lithium, cobalt that are common in batteries. A lot of folks are familiar with that. Obviously, what you mentioned in rare earth are things like, I'm probably getting this wrong, but like neodymium, like there's stuff
That's
like
right.
that are part of permanent batteries that go into everything it feels like we use today, including wind turbines and electric vehicles. nickel, copper, graphite, all these things are also exceedingly and increasingly important in the clean energy transition because they're raw materials that go into things like batteries, but also solar modules and wind turbines and electric vehicles and computers and defense materials. Yeah. I imagine there's a whole list. I know vanadium is one because the battery industry that is familiar with flow batteries would know that vanadium is a key, one of the key resources in a lot of flow battery applications. And the list goes on, truly does. Can you talk to me a bit about how you all identified the business opportunity that effectively is ReElement Technologies? What's the primary focus of ReElement Technologies, specifically around deploying scalable, efficient, versatile refining as a platform for rare earth elements?
It started about 9 years ago. From a business perspective, the core of what we do is separate and purify those critical minerals on the periodic table that are in high demand, that are under a lot of export controls today. And it comes down to getting them into manufacturing grade forms. You don't put rock into your cell phone. You have to turn ore or rock into chemical. Chemical turns into metal in a lot of ways. Sometimes chemical goes into a battery, and those things go into your technology applications. Going back to my team, we were started this in, dates back, I would say 2015, 2016 timeframe, which goes back to your introduction on coal and coal mining. We saw an opportunity in the broader infrastructure markets to take a contrarian play on rolling up coal mining assets to support global infrastructure growth through one of the primary inputs that makes metallurgical coal, which is a primary input that goes into steel. There was a massive secular downturn in the coal markets. Fracking was big. Cleaner, cheaper natural gas was becoming a larger part of the energy grid. So there was this huge secular downturn, massive amount of bankruptcies and capitulation in the coal markets, which put us in a unique position to acquire a large set of assets. Our backgrounds were more finance focused. We took an approach to, like I said, take that contrarian approach and roll up those assets and restructure those assets. Right. From the critical mineral perspective, because we didn't have generational experience in coal mining, we put a fresh set of eyes on the industry. And we understood earlier, I think, than a lot of folks in the supply chain of where those choke points resided and why China had the monopoly on the markets. And we looked at innovative technologies, driving this through innovation of how do you separate and purify critical minerals in a cost-effective way. Not just a science experiment to say that we can do it. Can we do it economically and sustainably? We looked at a variety, a dozen, if not more, technologies that are university systems being incubated at some of the greatest academic institutions in the world. A lot of them were focused on derivatives of solvent-based extraction methods. We didn't believe that was going to be replicable here in the United States for those reasons that I cited earlier. And we focused in on a technology that was being developed out of Purdue University that uses chromatography or chromatographic separation for the separation of complex mixtures that include critical minerals. We ended up acquiring that suite of patents focused on that critical mineral separation and purification. We produce high purity critical mineral outputs that we believe is at the low end or below the Chinese cost point. So that allows the United States and our allied nations to compete head to head and reshore manufacturing and secure national security.
So you're grappling with this real world problem of as a coal mining asset owner, a negative output is this low pH water. This low pH acidic wastewater discharge is an environmental challenge that every mining operation, and including coal, has to deal with. And I'm not sure how they dealt with it in the past, but what you recognize is like, hey, a lot of this stuff is actually critical minerals that if we could harvest them, there's an entire other value stream that we could be creating from this asset. So around 2017, you guys started cold calling chemical engineering departments to try to figure out, has anybody figured out how to do this yet? Can you talk about that?
Absolutely. looking at, can we extract that value from these waste streams? Again, being a little bit ahead of the curve on the critical mineral side of things, the market was just starting to develop. EVs were starting to take off. So you started to see more demand for energy storage and batteries, for magnets, things like that. I would also say geopolitics started to continue to heat up and ramp up. And the divergence between China taking our jobs and manufacturing base from the United States was really getting to a level that was unsustainable for our country. Let's just say it.
And you started seeing a lot in the news, 2018 to kind of 2021 timeframe around cobalt, like so much so that it forced Tesla to do an about face around what their sort of battery chemistry makeup was, right? Because it turns out that 99% of cobalt production in the world is owned by China. Predominantly in very socially inequitable situations. So keep going.
No, all of these massive macro trends on top of massive deficit spending and growing national debt, right? All of these things are mounting, and none of this is sustainable. So looking through a commodity lens at critical minerals, understanding what the choke point was, understanding processing of raw commodity from acquiring coal mining operations, operating them to a certain capacity. We looked at A, lowering our cost structure, B, creating value. So we started in, most of our mining operations were in East Kentucky. We had one in West Virginia, starting in our own backyard, calling University of Kentucky, West Virginia University, asking them what they were doing from research and development on capturing critical minerals from mine waste in coal country. Continued to network through that, asking questions. Who else is doing things? Knocking on doors, asking people if there's any way to collaborate. Can we sponsor research? Can we advance some of these efforts? Can we commercialize any of these technologies? And that's where I said we looked at a variety of different technologies that were being developed, being invested in from our government through the form of grants, R&D grants, going into our university systems. What was the government investing in at that time? And then we looked at, again, looking at the economic aspect of solvent extraction methods. Could that be applied here in the United States, or can it be applied outside of China? And some of that was more said to us rather than, some professors, scientists saying this will never be economical. That's not what we are purely running a science experiment here.
And you said, leave that to us.
Well, that started to get the wheels turning and saying, well, maybe we need to, if the expert's saying stay away from this from an economic standpoint, maybe we should, buyer beware. So we continued to go. And that led us, we were working on a sponsored research partnership on some acid mine drainage with Penn State University at the time. And we were looking at separation, purification, refining into ultra pure goods, chemical. And they said, you should talk to Purdue. And we're headquartered in the north side of Indianapolis. Purdue's in West Lafayette, about an hour and a half from us. So we reached out to Purdue University. Dr. Linda Wang, that ran the chemical engineering department, was utilizing chromatographic separation or chromatography for the separation of complex mixtures. Dr. Yi Ding, who is our chief technology officer today at ReElement Technologies, was a long time. Dr. Ding spent 7 years under Dr. Wang as co-patent of the patents that we ended up acquiring for chromatography for the separation and purification of critical minerals. So he was instrumental in the development of that IP for critical minerals. That's how we got to where we are today of looking, okay, this is, and what we understood is, I would say back in the 1960s, I would say chromatography was being looked at as the lead horse, if you will, of critical mineral rare earth element separation and purification. There just wasn't, there wasn't a market like there is today based off of advancements in technology. And then B, if you're going to ask a technical expert about chromatography, a lot of times chromatography is used as analytical chromatography to test the purity of product. It's not adaptable. It's too slow to change from one feedstock to the next. And the things that we benefit from are smart learning tools, simulation tools, things like that. Smart learning software,
right.
AI.
Things that computational power have allowed.
100% that enable you to make it a versatile platform for refining.
Fascinating. How long did that process take, Mark, from thinking we need to go find a chemical engineering solution to this to actually coming up with the acquisition of the IP from Purdue?
I'm going to go back with our team, right? I mean, you leverage the benefit of your team. And it did not take us long. We were very aggressive in that process. We quickly looked for a site to build our first plant to take this IP and demonstrate it at scale, scale. We leased a property or a facility in a light industrial strip mall in Noblesville, Indiana. We built it almost bespoke. I'll give a shout out to Jeff Peterson, who's our chief commercial officer, who shortly before that we hired him. He came out of the nuclear Navy, tasked him to his sleeves and start building this stuff. And he was a Purdue alum as well. So there was some easy collaboration that took place there. Sponsored more research at Purdue, broadened the IP into not just rare earth elements, but battery minerals, and then executed. Took that plant from running rare earth elements from recycled feedstocks, battery minerals from recycled feedstocks, classified it as a commercial qualification facility for multi-mineral, multi-feedstocks. So took in ores, concentrated brines, battery black mass, that is a shredded cathode that's been recycled. End-of-life magnets from a variety of applications, power tools, wind turbines, EV motors and rotors.
So effectively critical element recycling.
Yes. So we definitely started out of the gate on recycling because sustainability made a lot of sense to us, understanding the choke points, the need for these elements. We believe that growth curve was up and to the right. Supply was going to be constrained. These elements, even though they're called rare, they're not rare, but they are challenged in the market. You mentioned cobalt earlier, and there's other elements across the periodic table that are highly concentrated of where they're extracted in the world. So we could understand the competitive landscape of the importance of sustainability, if we can recycle them back into high purity manufacturing grade and put them back into the supply chain. That was a key objective of ours. That made a lot of sense for us. And then we can broaden the funnel to look at other type of feedstocks that are being mined, being concentrated, alternative feedstocks, now going full circle, that came out of mine waste, things like that. So that's where we are today. We run this multi-mineral platform, multi-feedstock. We think coal waste can be, and some of the coal waste that we've worked with, again, going full circle back to some of the university partners that we originally spoke to and reached out to, they produce some of the most interesting and high-grade feedstock that we have run. And that looks at from a market opportunity, both business-wise and from a national security standpoint. All the resources sit here within our borders that we will not have to permit a new rare earth element mine in our lifetime if you can do this economically.
Because you can extract all this from existing materials through the recycling process that you guys have innovated.
And that's right. And part of that is process engineering. Part of that is byproduct economics as well, by understanding what other monetizable material can you produce out of these waste streams as well. Coal waste, for example, has a lot of silica in its waste stream. It's high silica content. But silicon dioxide, if you can produce that, that is a ingredient that goes into the semiconductor space. So if you look at things like the CHIPS Act, things that the government are investing in, trying to reshore manufacturing of chips here in the United States, well, then those things make a lot of sense to us. So using byproduct economics to extract things like zinc and zirconium and silica, along with the rare earth elements, that gets very interesting as far as meeting the needs of our domestic supply chain, along with other elements across the value chain.
I think one of the fascinating things for me is you enunciated, well, a couple of things. Is one, you are able to be competitive on quality and cost, and you don't use this heavy chemical process that is traditionally used, that results in no acidic wastewater discharge, closed loop system effectively. And yet you're able to do this in a relatively small footprint. You operate on 7,000 square foot facility presently. That is light industrial. You share sort of parking space with facilities that don't suggest that you are providing some sort of complex chemical processing in the building. Can you talk about the modular nature and small footprint of the technology and how that contributes to the scalability of this business and the long-term prospects for ReElement?
I think it's where the rubber meets the road. It's why we can produce these commodities at a cost point that's globally competitive, where China controls these markets. And if China wants to control or drop the price, you can look at U.S. assets today that mine rare earth elements that have been bankrupt in the past, and they've been bankrupt through a couple times through different cycles because China's bankrupted them. They've chosen to drop price points, oversupply the market, and make those assets unsustainable. Those assets exist today.
Yeah,
they are not immune to those same practices and same economic headwinds, if you will. Chromatography is like you suggested is much different. We do it in a small footprint. If you compare the two processes of how and where things are refined today, and the processes that they use versus how we do things today, solvent extraction methods uses what they call mixer settler units. For example, a neodymium, ND or PR, neodymium or praseodymium, which are two highly important ingredients that go into rare earth permanent magnets. They are considered light rare earth elements on the periodic table. To separate some of those light rare earth elements, it might take 100 stages. So 100 separate mixer settler units. So 100 stages to create that separation and purification of those elements. So you're talking all that CapEx has to be incurred up front. Each of those mixture settler units has the chemical, highly chemical dependent to create slight pH adjustments to dissolve those metals or dissolve those elements at slightly different pHs where you can then achieve separation. It's a way oversimplified way of explaining it. But a heavy rare earth element like terbium or dysprosium on the periodic table might take up to 1,000 stages, 10 times that of a light rare earth. So same deal, CapEx that out of the gate. You have to build to a nameplate capacity. You have to operate to a nameplate capacity, meaning you have to feed that thing constantly. That is highly CapEx on the front end. OpEx is high as well because of all the reagents that go into the process.
Yeah.
And then on the back end is a lot of acidic wastewater discharge that if you're going to operate this thing in the United States, that you're going to have massive wastewater treatment facilities. And that's all going to contribute to higher cost output. And then if you want to hire technical people at United States wages versus China wages, that's why these facilities do not exist in the United States. And in my opinion, they never will exist in the United States. Many of companies have tried to do that. There is one that exists today in the United States through bankruptcy. It was inherited. They continue to try to operate it, and I believe they lose money on an annual basis trying to do that at a 55, 56 NdPr market today. They're not economically sustainable at those prices. So That's the conundrum. That's the problem. Chromatography, we can achieve about 100 stages in one column.
What does that mean? A column?
A column is we use column-based system cylinders that are packed with resins. These resins have these are off-the-shelf equipment. Because chromatography is it's not a novel or new technology. It's used across a variety of different industries. Going back to our roots with Purdue University, this technology was built between Purdue. The foundation of this technology was built between Purdue University and Eli Lilly for the production of pharmaceuticals. This foundation of this technology was licensed to the food and beverage industry for the purification of fructose and glucose sugars. It's how a lot of these products are produced today in pure form. So these are off the shelf, US based components that you buy. And like I said, one column packed with resin replaces about 100 stages of solvent mixer settler units.
What's that look like from a square footage savings perspective?
Oh, massive. I mean, we can operate in let's just call it I'm going to back of the envelope ballpark this call it a 50 foot by 50 foot, space of columns, which would replace, a football field of two of mixer settler units. So much more compact because you're taking.
So let's just call it a tenth of the space, the end zone versus the entire field.
That's right.
Wow.
That's a good way to put it.
Okay.
So we're able to do this at a much smaller footprint, and we are not. There's a chemical process. We do use chemical in our process, but a lot, like you said, closed loop. A lot of our chemical is recaptured. So that column is packed with resin. And then we classify. There's three stages. There's the front end. There's the separation and the chromatography phase, and then there's the back end conversion into chemical product. The front end is high. It's high impact brute force. It's turning solids into liquid. There's nothing really proprietary that ReElement Technologies does today. We use industry standard mechanisms and processes to turn solids into liquids. There is a leaching phase. We use acids. We capture a lot of our acids and reuse them. You're using mild hydrochloric or sulfuric acid and turning metals or solids into liquids. You're doing a filter of that liquid. So you're then getting what we call a pregnant leachate that is injected into the top of your column, which flows through your column, and your resins, which we would classify them as kind of feeling like a kinetic sand that a kid would play with. Sometimes very fine, have a lot of surface area. They're porous. These resins have a affinity or a lack of affinity for the elements that you are focusing on. So they will go through the column. They will
attract it or reject it.
Be attracted to these. And now it's then you loot your column and you knock off elements in very distinct phases. There's separation of these elements that occur, or sometimes these elements will move. Another way of putting it, these elements will move through the column at different speeds
based on their weight,
and their affinity, their attraction to these. Yeah, exactly. So then you can measure the output purity of your element. So we can go back to the magnet metals of Nd, Pr, Dy. On the periodic table, you know exactly the pure band that you're getting. And there are mixed bands, so they're not as pure, but you can put them right back into the top. So we use
a refining process. Yeah.
So we use advanced forms of chromatography, continuous chromatography, simulated moving bed chromatography, which can continue this. So you're taking mixed bands, putting them right back into the column, and you're constantly getting separation phases, eluting phases, which are discharging, and then regeneration phases of your column. So you're constantly running this refining process. And doing it in a small footprint without the harsh chemical inputs.
Right.
We use water in our process. It's an aqueous-based solution. Whether we use more or less, doesn't really matter to us because the chemical reagents aren't in our water that we discharge. So it's much cleaner. We don't have the acidic wastewater, toxic wastewater discharge problem that a solvent facility does have.